Thank you, and good morning to everyone here. This is the work we've done on hardening containers with static and dynamic analysis, which is a section of cloud security. So now let's come to the main question, which is why cloud security? So over the recent few years, we have seen that so many companies or so many researchers have been exploring the domain of cloud computing, and that has led to so many advancements. And as expected, any technological advancements that are being made in a field will naturally open the attack surface. As you have so many technologies being integrated, you have so many new things being learned and so many new things being exposed out to the public or to other companies as well. So that obviously raises the important question as to how secure can we make it, or how do we make sure that as we grow, the security grows with it as well. And hence, cloud security becomes something really important, especially in 2022. And that's why we have taken container security as our topic. So the process that we have followed for this project would be so we developed an all-round security hardening guideline and policy for containers. We had received 2 containers from a company that we were collaborating with, and those were the ones that we hardened. So the product for which the guidelines were developed, they followed a microservice architecture, and hence naturally there were multiple Docker containers involved. And the project took place in 2 phases. So the first one was a static phase where nothing was really happening in terms of container runtime. And second was the dynamic phase where the containers are actually running and we analyze the containers while they run. So we can, let's say, run a few scripts, we can check what system calls are being made, we can see their runtime activity. So that was the dynamic analysis phase. So coming to the first phase, we worked with a few open source tools, mainly for benchmarking, static scanning. These were the main activities that we wanted to carry out in the static analysis phase. So Docker Bench is what we used as the benchmarking tool. We used Anchor and Trivy, which are static analysis tools. And we just wrote a few custom scripts that aided us in our static analysis. Now, in the second phase, which was the dynamic analysis phase, we used tools called Sysdig and Falco, which was again aided with a few Python scripts that we wrote, which helped us with the automation and a few comparisons. So Sysdig and Falco are also monitoring and alerting service tools that are open source, at least a part of them. So that's the one that we used. And we finally came out with a detailed hardening guideline based on all the analysis that we had done. So here is an overview of the first phase, which is the static analysis phase. We have a remote registry from which we pull the images, and then we download them onto our local system. And now comes the actual static scan part. We have Anchor and Trivy both set up on our system. Anchor uses NVD, the National Vulnerability Database, and that it has to sync and download entirely on your system. So Anchor usually takes a while to set up and get go, whereas Trivy actually uses its own database, which is a collection of a lot of different sets. They do not install this on your local system. So this is a remote database. Hence, it's fairly quicker. It just has to cross-reference with the remote database, nothing to do with your system or downloading. And once these 2 scanners are done with their scans, we get the output. They both provide a neat, detailed column row split output. And over here, we deploy our script, which is a Python script which analyzes both these outputs and gives us a total count, a comparison report, and basically helps us decide which one is better, how one performed in comparison to the other, etc. And that is what we analyze on. Now we come to the second part, which is dynamic analysis. So in dynamic analysis, what we do is we actually run the containers, and then we try to form a whitelist, and anything that comes outside the whitelist, we try to alert the admin. So coming to the first step, we monitor system calls that are being made to the host OS. We do this using sysdig, as mentioned in the second slide. And once the monitoring actually begins, we see the kind of system calls and programs that are being executed, that are being told to the host OS to perform, and so on. So we extract all of these and we form a whitelist. So how this works is, now that we know what the containers are supposed to do, in the test environment, we do exactly just those things that the container is meant to do. We test only the functionalities that it is supposed to perform and nothing extra. This way we get a neat whitelist of what should be allowed to run in the container and nothing more. So once we have this detailed whitelist, we change the Falco's default config file. So Falco is a monitoring and alerting service. So in the default config file, if we mention the whitelist, it'll only allow those system calls and programs to execute. And now that we have changed the file, we can fire up Falco. And this is the procedure that it follows. If the call is in whitelist, then there is no reason for Falco to alert the admin. Hence, it just continues monitoring. If not, it will alert the admin and then proceed back to monitoring. So this is an example Falco ruleset. So the list, or the whitelist, is in this case a syscall white, which stands for system call whitelist. And the items in which we have given in this example is open. So that means the system call whitelist contains just one system call called open. So any other system call that, basically any system call that is not open, will be flagged by Falco and will alert the admin. So next we have a rule, which is basically to detect a syscall. We have a description that this syscall is banned because it's not in our whitelist, and how actually this will pick up that system call is in the condition field. You see that we do container ID is not equal to the host, basically that the container has ran this, and not event type in syscall white. This is basically just a syntax thing, which it's just a Falco syntax. What it means to say is that if the event type, which in this case is a system call, is not in the specified whitelist, then this condition would match and it would alert the admin. So the output would be syscall ran inside kernel, and the syscall would be the event type, which in this case would just be the system call that should not have run. And priority over here we have given as informational, but let's say you want to bump up the priority and you want something to be flagged as emergency. We do not do that here because we have our whitelist, and we do not want to proceed with the blacklist because whitelist is one of the best ways to secure your containers, since you don't really know what exactly to blacklist. The list of blacklisting items can always keep growing, but since you know your functionality, a whitelist would be perfect. But in case you want to use an emergency priority, what we can do is just make another blacklist and put in a list of severe system calls that you know you are not using. And if any call is being made within that list, which would be the opposite of this condition, then you would bring up an emergency priority. So coming back to the static analysis phase, these are the results that we get from the anchor scan. So we call the backend, so since I mentioned that we had two containers to test, we call the backend container an API container, and we call the front-end container the view container. So in the API container, you see a significantly higher number of vulnerabilities that are catched, although be it they are negligible, but that's still a considerably higher number than the view container. That's because we have a lot of processing functionality in the backend container as compared to view. Hence, we see a much larger number. But on the other side, we see the number of critical vulnerabilities are fairly low in both of them. So only thing that the main inference that we draw from here is that the backend containers have a lot more processing to do, hence we get a bigger number of vulnerabilities. Now we come to Trivy, the second tool. And over here, we see it follows a different severity rating. We have critical, high, medium, low, and unknown. So in the API container, again, it follows the same trend as expected, but over here we see that the number of vulnerabilities itself caught is slightly higher. So hence we can say from our experience that Trivy was actually a better static analysis tool because it has actually caught a better number than Anchor. But we also see that the number of critical vulnerabilities that Trivy ranks as critical in its severity rating is also slightly higher compared to Anchor. And that's honestly better because you would rather be safe than sorry. Hence, we would rather classify a vulnerability as critical than high or medium. So what we do in our script as well is once we cross-reference the results, if there's a mismatch in the severity rating, which most likely will be there because they do follow different rating, we always assign it to the higher severity ranking because that way you're better off taking higher action than taking lower action for a certain vulnerability. Now we come to the dynamic analysis results. So we have split this as well. Even this dynamic analysis, though it is phase 2, in phase 2, we have two phases. One is a pre-launch phase and one is a post-launch phase. So pre-launch phase basically means while the container is while it's booting, while it's being fired up, we run the monitoring service, and then we stop it once the container is set. And then we start it again, which becomes the post-launch phase, where we run our tests, where we check the functionalities, and then we stop it again once we have fulfilled all the tests that we wanted to carry out. So in this, we see that in the pre-launch phase, the number of vulnerabilities are much higher than the post phase. This is because while booting, you see that the containers make a lot of system calls to get their resources, to get ready for execution, to be set. Hence, the pre-launch phase has a large number of vulnerabilities, a large number of system calls that it's making as compared to the post-launch. And post-launch, we just see about 36 for API and just 22 for Vue. And naturally, the same trend goes here as well. In Vue, there is not too much functionality to be followed. Hence, the overall number of system calls that it's making is lower, and API is the one that's doing majority of the processing. So coming to the end, and if I were to just summarize what we have done, we tested both the containers, we used Anchor and Trivy, and we made a whitelist, and we alerted the admins when these calls were not in the whitelist, and we were able to develop a hardening policy for these containers out of everything that we have analyzed and processed. And when we talk about the main takeaways, that would be vulnerability assessment tests, which we have run. There have been simple updates and patches that you should be doing. So these takeaways are basically for anyone that is looking to make their container secure. We would encourage you to follow these steps, which include, again, as I mentioned, assessment tests, simple updates and patches. These go a long way. Then we have port closing, which we checked, enabling TLS, monitoring system calls, which was the main part of what we did in phase 2, and formulation of whitelists. And as mentioned, blacklists are usually not the way to go because you will never know what system calls to not permit, because you always have to assume that a hacker or a perpetrator would be well equipped to find out new ways. So the best thing that you can do is to make a whitelist, as you know best that your container or your application should run a certain way. So make sure that you just allow those system calls to execute, those programs to execute, because that's what you have seen, that's what you know. You don't know the other side. So blacklisting is usually not preferred. And there's a wide range of security hardening, and teams can use the hardening policy that we have developed to achieve the desired level of security for their containers. So coming to the future scope, these are just a few small things that we can think about. Automate the entire process to ensure end-to-end continuous monitoring for quick response to any alert. We have done small amounts of automation throughout, but yes, it would definitely be a big plus if this was, let's say, a complete static plus dynamic analysis end-to-end too. And next thing that we could think about is just blocking the calls instead of alerting the admin. This can be done with seccomp and Docker Compose support. But one reason we did not do it for now is because, let's say there is a certain system call that has been executed outside our whitelist. It may not exactly be malicious. It might actually be needed. It might have been missed in your tests, or it might be a new functionality that we haven't yet checked the complete extent or the complete boundaries of. So that way, if you just block it, then you would hamper the runtime, you would hamper the functionality, and the container might just stop or shut down, or it may not just, that functionality may not work as desired. Hence, we went with this approach where we alert the admin, and the admin should most likely be well versed with the functionalities, and he or she may know what to do. And the last step would be to create a master tool that implements these guidelines and deploy a hardened container from a given image. So this would be a separate step. This may not be related to the work that we had done on making this. So this would be a tool that would take the final guideline and then help in deployment. So that's it from my side.